Hello everyone. Today we're gonna study the Pythagorean theorem, and we're gonna make a proof of the Pythagorean theorem using Euclid's proof. So the Pythagorean theorem says that the larger square is equal to the sum of the two smaller squares. And if we remember, in the middle school we studied that in a right triangle we say that c square equal a square plus b square. So to begin with the proof, let's start with the construction using GeoGebra. So we're gonna construct a triangle that would be ABC, which is gonna be a right triangle on C, and a right triangle here. And so from CB we're gonna construct a square CBDE, and then from AC we're gonna construct a square ACHI, and then from AB we're gonna construct a third square ABGF. And to begin with our proof we must add some more constructions. So let's draw a segment that will be parallel to AF, so that we have AF parallel to CG as shown here, and this is how the drawing looks like. Now, in order to prove the Pythagorean theorem, we need to prove that the small square ACHI is equal to AKJF, and then the squares BDEC is equal to KBGJ. Let's start with the first squares AKJF and ACHI and prove they are equal. To do this, we need to draw a line from point C to F to create a segment CF and a triangle ACF. Then draw a second line from point I to B to create a segment IB and triangle AIB. The first thing is to prove the triangle ACF is equal to triangle AIB. We know that ACHI is a square. That means, by definition of the square, that all sides are equal and all angles are right angles. With that being said, AC is equal to IA, and IAC, the angle IAC, is a right angle. Same thing goes with the square ABGF, and we get AF equal AB, and the angle FAB is a right angle. Since we have two right angles, and according to the right angle congruent theorem, we get if the angle FAB is congruent to angle IAC, and by the reflexive property of equality, the angle CAB is congruent to itself, and by the addition property of equality, the angle FAB plus the angle CAB is congruent to angle IAC plus the angle CAB. Now, FAB plus CAB is CAF, and the angles IAC plus CAB is just the angle IAB. Therefore, the angle CAF is congruent to angle IAB. So now we have all the information we need to prove the congruence of triangles ACF and AIB. So we proved that AC is equal to AI, and AF is equal to AB, and angle ACF is equal to angle IAB, and according to angle side postulate, SAS postulate, the triangle ACF is congruent to triangle AIB. There is a theorem that says if a parallelogram and a triangle are on the same base and within the same parallel line, then the area of the triangle is half the area of the parallelogram. And in our case, we see that the triangle AIB and the square ACHI share the same side or base AI, and they are within the two parallel AI and CH or HB, since the points H, C, and B are collinear. Therefore, according to the theorem, ACHI is equal to 2 of triangle AIB, and we're talking here about the area. And the same thing goes with the triangle ACF and the square AKGF. That share the same side or base AF, and they are within the two parallel lines AF and KJ or CJ, since the points CK and J are collinear. Therefore, according to the theorem, AKJF is equal to 2 ACF. In the first part of the proof, we already proved that the triangles AIB and ACF are congruent. So we substitute from one of the equalities above, and we get ACHI is equal to 2 ACF. So we substituted AIB with ACF. So from 1 and 2, and using the transitive property, we get ACHI is congruent to AKGF. And now we prove that this square ACHI and AKGF are equal. So after proving that ACHI is equal to AKJF, we will follow the same process to prove that the squares EDBC is equal to KBJC. So the first thing we do is we're gonna draw line CG and line AD, and then follow the same process until we prove that the triangles CBG and ABD are congruent according to the side angle side postulate. So we have CB is equal to BD, and BA is equal to BJ, because this is a square and this is a square, and all sides of the squares are equal. And then the angle ABD is equal to the angle CBG, and according to the side angle side postulate, and we're gonna prove, we'll find that the triangle ABD and CBG are congruent. And then, using the theorem of the parallelogram and the triangle that share the same base and same parallel lines, we find that the triangle CB or the triangle ABD is equal to half the square BCED, and the triangle CBG is equal to half the square K, or the rectangle KBGJ, and we already proved that the triangle ABD and the triangle CBG are congruent. So using the substitution property in the first equation, we get BCED is equal to 2CBG, so we just substituted here the ABD with CBG, since the CBG and ABD are equal or congruent. And from 1 and 2, and using the transitive property, we conclude that the square KB, or the triangle KBGJ, and the square BCED are equal. So we finally proved that the square ACHI is equal to the square AKJF, and the square KBGJ is equal to the square BCED. And since AKJF plus KBGJ is equal to ABGF, as you see here on the graph, you see AKGF plus KBGJ is equal to ABGF, and using the substitution property, we find that ACHI plus BCED is equal to ABGF. So we just substituted AKGF with ACHI and KBGJ with BCED, and we conclude that it's equal to the big square. So therefore we prove the Pythagorean theorem using Euclid's proof, and the Pythagorean theorem that says in any right triangle, the square opposite to the right triangle is always equal to the sum of the two other squares. And that's it for today.